This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody, and welcome to our 8th week in Algorithms for Functional Genomics. This week we're going to talk about dimensionality reduction, which is a very important step in machine learning, but also a very important general tool for data analysis and data visualization. But before we get into that, let's just try to deal with this recurrent matter, which is our replacement lecture for the 27th of September. So, as I explained last week, we had a lecture that was booked by mistake to a university holiday, and I finally managed to get us a replacement lecture. So that was next Friday. That's not going to happen. The following week is the mid-semester break, so we won't have any lectures or tutorials. The following week we will have this replacement for this lecture. That's going to take place at the chemistry building at the senior theater. It will go from 1 to 2 p.m. on Monday, 7th of October. And since it was a Friday, we also had 2 tutorials booked. These tutorials were then replaced for the following day, so Tuesday, 8th October, and we have 2 sessions there, so 10 to 11 and 11 to 12. And they're going to take place at the Electrical and Electronic Engineering Building, room 121. Please make sure you're familiar with the place before getting there, and make sure to be there. And I'll post this on LMS as well. So we're going to talk then this week about dimensionality reduction. And just to give us an overview of what we're going to talk about, we're going to talk about what it is and why do we need it, but also we're going to try and approach it into 2 different ways. So dimensionality reduction, we can talk about it via feature selection, and today we're going to introduce one important algorithm for feature selection, which is called greedy feature selection, and also we're going to talk about feature extraction. And we'll focus on unsupervised and supervised methods. And today, we're going to focus on 2 main methods, the very famous principal component analysis, or PCA, and singular value decomposition, or SVD. So dimensionality reduction. So many modern data domains involve huge number of dimensions and features. So we live in a post-big data world. So it's very common to identify data sets with a huge number of features to deal with. For instance, documents with thousands of words, images with millions of pixels, and even in genomics, we're usually dealing with thousands of genes, millions of DNA variants, and so on and so forth. So dimensionality is a very important problem for us. For instance, just as an example, if we consider a gene expression microarray, and let's say we do that for a genome-wide assay, that would involve 27,000 genes. Let's say if we consider this plant here, which is Arabidopsis thaliana, was the first plant to have its genome sequenced, and we want a microarray involving every single gene of that plant. And let's say we want 100 samples, and alternatively, let's say we have a pathogen with a few strains that are drug resistant, a few strains that are susceptible, and we want to identify for every single gene their expression levels to identify if any gene are actually related to that phenotype. So we end up with quite a few dimensions. For instance, if we consider this data set, what's the dimensionality of the data set? We have 100 samples, and we are looking to 27,000 genes. So therefore, the dimensionality of our data set is actually 27,000 dimensions. If you ask me, that's 26,997 too many, mainly because we can't visualize them, not all at once. So why do we need dimensionality reduction? So with high dimensionality, it can come a lot of interesting things. So we can learn a lot about biology, but also it comes with a lot of costs associated with it. For instance, as mentioned, we have an inherent difficulty in data interpretation and visualization given the large number of dimensions. So our world is 3-dimensional, 4-dimensional, if you consider time as a dimension. So we're usually limited to plotting either 2 or 3 variables at a time. So how do we access thousands of variables? How do we visualize them? Or how do we bring all that information together? Because we don't want to do all permutations and combinations of pairs of variables and visualize them individually. We want to have a global picture. So how we bring all that information together into 2 or 3 or a few dimensions. Also, that with dimensionality comes a lot of redundant and irrelevant features. For instance, redundant features would be features that are correlated. For instance, if you're trying to describe a protein, you can extract a feature that is protein sequence, length, for instance, how many amino acids the sequence has, and also the molecular weight of the protein. And these 2 variables will be somehow connected. So you're measuring slightly different things, but they will be correlated. So you might have a bit of redundancy there. And also variables or features you consider, they could be completely irrelevant. So they might not be helping you explain the phenomenon you're observing at all. And the effect of these 2 things that it has on machine learning algorithms, which we will discuss on week 12, is degrading performance. So we don't want more than we need. So that comes back to Occam's razor's principle as well. So this in machine learning is usually noise. So information that is not helping you. And it's actually degrading performance of the algorithms. So, and with dimensionality also comes the computational costs that in certain cases might lead to an intractable problem. So for instance, let's say you have a huge data set with a lot of dimensions, and the algorithm you're using scales cubically. So actually, that could make things very, very difficult to process. So if we can reduce the number of dimensionalities, maybe we gain a lot of time and processing time and memory usage as well. And with all that, we also have something called curse of dimensionality, which sounds really bad, and it could be. So curse of dimensionality is the following. So that's a term coined by Richard Bellman in the 60s. If you don't know who Richard Bellman is, he's a very famous mathematician, one of the first computer scientists. He created the Bellman-Ford algorithm for shortest path in graphs. And very brilliant guy, but he also responsible for something that we've been talking a lot, which is he introduced the concept of dynamic programming as well. So this is just a term coined by him, and it refers to problems associated with multivariate data analysis and what happens with that when dimensionality increases. So we'll have a simple toy example just to try to exemplify what happens when we increase dimensionality and the main things we need to be careful about. So this is a very simple example, and it's a very, very inefficient way to go around to solve it. But even if you get a very efficient way to do it, you still have curse of dimensionality, as I'm going to try to explain. So let's consider the following problem. So we have a pattern recognition problem. So we have a bunch of objects, and we want to bin them in 3 different classes. So we have 3 different types of objects that have been classified based on a single feature. Let's say we only have a single feature to describe that object, and let's call it x1. So based on x1, each of the objects lies like this on a unidimensional vector, okay? So basically a very, very rudimentary algorithm to try to separate these 3 classes. So a classification problem would be, and this is again saying it's a very inefficient way, would be to divide the feature space into uniform bins. So let's say our features goes from here to here on this vector. Let's break it down in 3 different bins as we have 3 different classes, okay? And then we will compute the ratio of the examples for each class in each bin. And for instance, the dominant class in this case is the red circle, and then we'll call this bin red circle. In this case, the dominant one is the green square, we call it green square bin, and in this case is the blue triangle, we'll call it blue triangle bin. And what happens is for new data, if we don't know what the data is, let's say a new data lies here, we're going to call it the same label as the predominant data. That's how our classifier would work, okay? So we started with 1 feature and 3 different bins. So the issue is that we still have a lot of overlap between the classes. So if you build a model, a classifier with just 1 feature, it's probably not going to be a very, very good, very predictive model. In this case, each bin has one mistake, so one object that shouldn't be there. So if we calculate quickly a classification metric, so performance metric, let's say accuracy. Accuracy is the proportion of the instances here that are actually correct, and in this case, we have 9 instances. 6 of them are in the correct bin, so we have 6 out of 9 correct, so we have a 67% accuracy. But that means with just one feature, we have a lot of overlap. So let's say that to increase predictive power, we decide to incorporate a second feature. So let's say we're classifying protein sequences into structural classes. Let's say this is simply alpha helical contents. Let's try to consider a different one, a second feature. And if we continue with the same binning approach, what that is going to affect us is we're going to go from 3 bins to 9 bins because we added another dimension. Okay, we're still dividing the space, the search space in the same way. And this creates one problem and refers to these questions. Which should we maintain constant? Do we maintain the density of the examples per bin constant? In this first case here, we have 3 examples per bin. And if we do that, we need to increase the number of examples we have to start with. So it goes from 9 to 27 to have the same constant density between bins. That's not usually feasible, or you might not have the data to do that. And alternatively, we'll keep the same number of examples. And if we do that, what we end up having is a very sparse scatter plots of the features in 2D space. And if we move to 3 dimensions, that makes it worse. So the number of bins necessary goes to 27. And to keep that density, we would need to grow the number of examples to 81. The number of examples, if we keep it the same, we'll end up with a scatter plot in 3D that is very, very empty. So things that we can see from here is that the number of bins is growing exponentially. The number of examples required to maintain density grows exponentially as well. And if we don't have enough examples, we end up with a very sparsely populated search space. So the implications of this curse of dimensionality is basically that we do have an exponential growth in number of examples that are required to properly estimate a given function in a search space. And what that means in practice is, especially for machine learning algorithms, is that for a given sample size, there's a maximum number of features that I can consider above which the performance of the classifier will degrade rather than improve. So if we keep adding features to a classifier that will try to classify those objects in 3 bins, what's going to happen is we're going to have an increase in performance, and then eventually we'll keep adding noise, and this performance will degrade. So what we do to overcome dimensionality, we try to reduce it as much as possible. So we want the simplest model as possible. And one of the assumptions of that is that most of the variations, the intrinsic variations and structures of the data are contained on a usually small subset of dimensions. And perhaps if we remove or simplify these dimensions without losing information, we are in a good position. So we do have 2 main approaches for dimensionality reduction. And we're talking about dimensionality reduction. We start with a search space or a feature space with n attributes, and we want to go to a search space or a feature space with m attributes, where m is smaller or considerably smaller than n. And the first one is called feature selection. And basically, what feature selections means is, out of all features I'm considering, I'm going to choose a subset of those existing features. So we have something like this. I have n different features to describe my problem, and I'll select a subset of those based, for instance, on an objective function. Alternatively, a different approach for dimensionality reduction will be feature extraction. That's different in a way that instead of choosing existing features, we will create new features by combining existing ones. Okay? So basically, what we want with feature extraction is, given our initial features, identify a mapping function f that will generate new features for us. But in either case, there is a main goal, which is a common goal to find a low dimensional representation of the data. And at all costs, we want to preserve the information and the structure of the data without losing important information as well. So for feature selection, so we do have something called supervised feature selection. Supervised feature selection aims to optimize an objective function. So that's valid, for instance, if you have a classifier that you know what are the labels of your objects. You know if your object is a red sphere or circle or a green square, for instance. And the objective function in classification, for instance, in that case was, for instance, accuracy. And if accuracy and classification is basically, classification is a problem that you want to predict labels, and regression is the problem that you want to predict actual numbers. So one is qualitative and the other is quantitative. And there are a couple algorithms for supervised feature selection, and some of them are backward greedy feature selection elimination, and the other one forward greedy feature selection. Okay, what does that mean? So they are both greedy algorithms, so they are making local decisions, and one is aiming to eliminate features, and the other one keeps increasing the number of features we are considering. And let's now just focus on forward greedy feature selection to start with. So forward greedy feature selection will work as follows. So we'll start with a bag of features, all features we have. So we have n features. We start with all of them. And we have a second bag, which is the features we are going to remove from this first bag and put on the second. So what we start doing is we're going to evaluate each feature individually. So we're going to choose the feature with the highest score individually. Okay? What we're going to do then is add these features to the second pool, and then we are going to rescore considering that feature fixed and the combinations of that feature with all other n-1 features. And then we repeat the process. We'll, out of those pairs, which is the best one, we'll fix it, put in the pool, and repeat the process until we have a sequence of additions of features. And the basic algorithm looks like this. So we'll start with two bags. One bag of features with our initial features from 1 to n. One bag of feature selection, which doesn't have anything to start with. And basically, we're going to iterate through all of them. So we're going to do this n times. And at each time, we're going to evaluate all the features individually. So let's say we got here on the first iteration. The first iteration will basically evaluate feature by feature, keeping track of which one is best. So we keep track of the best score and what's the best current feature. So after this, we basically ask the question if we had improved the global maximum, and basically we include that best feature in the feature pool. And we remove that feature from that feature pool. And on the next one, we already will have one feature on FS, and we'll consider combinations of that feature with all the others. And this keeps going. And as you can imagine, so in the first iteration, we are considering each feature individually. So in terms of number of evaluations we need to do, the first round we do n evaluations. After we fix one, the second round we do n-1 evaluations, then n-2, and so on and so forth. So the time complexity for this is, again, as a greedy algorithm, quadratic for either backward or forward. So the difference between the backward and forward greedy feature selection is the backward, we start with a complete subset, and by removing one at a time, we evaluate what's the worst score. And we remove the feature that is not contributing for accuracy, for instance. But we also need to consider the evaluation costs. So in terms of the number of times we need to evaluate the methods, that's quadratic, but also we need to consider the evaluation time. And for instance, that could be quadratic as well. And then we have a very, very expensive algorithm there, which might be unfeasible, depending on your data set, depending on the algorithm you chose to evaluate. So if you have a lot of features, it might take a long time to evaluate them. And alternatively, what you could do is stop after selecting or removing k features. Or stop when your objective function stops improving. So as mentioned, there is a theoretical limit where you keep adding features and that's not going to improve your performance, and you have usually a graph that looks like this. So you keep improving performance as we increase the number of features we are using, and at some point what we're actually using is noise or redundant data. And that's not only it's not going to improve performance, but performance will decrease in time as well. So we can, for instance, stop here. So looking now to the other type of dimensionality reduction, it has to do with feature extraction. In feature extraction, instead of just selecting a subset of features, we want to create new features. And to do that, we're going to define a mapping function, y, as a function of all features we have. So let's say we do have those n features. We want to find a mapping function that's going to combine those features in better ones. Okay? However, the optimal mapping, that mapping that will be better for your problem, that's one problem dependent, and that's not usually a linear transformation that is required. However, most of the feature extraction algorithms are commonly limited to linear projections. What does that mean? So I want the mapping function y that it's going to modify our initial data x by using a linear projection w. Okay, so this is basically a matrix notation. So we have our initial sets of features here from x1 to xn, and we want to generate, using linear feature extraction, generate a new one, y. And for that, we are going to find a linear projection, which is this matrix here. And the projection is done by multiplying this matrix by our original data. So we're projecting this on a new search space. Okay? So is people familiar with matrix multiplication? Do you know how to multiply a matrix to a vector? Yeah? So basically, just a recap. So you multiply a matrix n by n times a vector of size n, we end up with a vector of size n. And the first element, y1, is the multiplication. It's obtained by multiplying w11 by x1 plus w12 by x2, and so on and so forth. And the second one is multiplying this line by this vector. Okay? But the question is, there are virtually infinite number of potential linear projections to derive our data. And the question is, which one to use? Which one is best? And there are two criteria to find the best mapping function. So the first one is, again, supervised. In a classification task, for instance, I'm interested in finding a mapping that will separate two classes or more classes. And an example of an algorithm that uses that we'll talk about on Friday is linear discriminant analysis. And for instance, in regression, we're aiming to maximize the correlation between the projected data and a given target variable. And an example of an algorithm doing that is partial least squares. Alternatively, we can do that without looking at our target class or target variable, which will do this via signal representation, which is an unsupervised technique. We just look at the actual data. And the goal for signal representation feature extraction is basically retain as much data variance as possible when we reduce the number of dimensions we have. And the two main methods for those are principal component analysis and singular value decomposition. And we'll focus on those two for now. So principal component analysis. So imagine we have sets of points scattered in multidimensional space, let's say in 3D here. And the main idea is we try to find a more compact representation of the data. Let's say it's a 3D plot, but we want to represent it only in 2 dimensions. Okay? So for that, we can use PCA, which is a widely used method for unsupervised linear dimensionality reduction. It's unsupervised because it's only going to look at the features, not the target we're looking at. And it's a linear transformation, meaning what we're going to do when we do the transformation is we're going to do a linear combination of attributes. And the main goal for PCA is to find, let's say, k-dimensional sets of bases or vectors called components, such that if we project our data in this new subspace, we retain as much variance as possible. Okay? And K here, considering that K is smaller than the dimensionality of our original data set. And PCA has a lot of applications. One of them, of course, is data visualization. Let's say we want to go from a 100-dimensional space to a 2D or 3D space. That will help a lot in making the plots and visualizing the data. It's quite very, very useful on data compression as well. For instance, if we're interested in removing redundant dimensions, so dimensions that are linearly correlated, for instance. And signal processing has been used a lot to separate uncorrelated signals, and also to remove noise, and also to assist machine learning algorithms removing noise as well and improving performance. And with that, improving running time as well. So PCA, in other words, involves a mathematical procedure that transforms a number of possibly correlated variables into a smaller number of uncorrelated variables, which are called principal components. So what's a principal component? A principal component is basically a projection that maximizes variance. So let's consider this data here. So we have two variables, x1 and x2. And that's how our data is distributed. Okay? So our principal component in that case will be a vector that points to the maximum variability of the data. In this case will be this vector z1 here. Okay, so the first principal component is a projection or a direction that maximizes the variance of the data. So if you look at the data, most variance is across here, so going through the origin from sector 2 to 4. The second principal component will be then also a projection direction that is orthogonal to the first. Orthogonal meaning it needs to be 90 degrees from the first, so completely independent from the first, that maximizes the variance of the projected data. Okay? So the principal components then are orthogonal vectors. And what this does is basically the spatial rearrangements that may review interesting relationships that were hidden in higher dimensions. So it's quite interesting for that. And the conceptual algorithm for PCA then works as follows. First thing we got to do is, let's say we consider this simple example in 2D, we'll find a line such that when the data is projected to it, it has maximum variance. It will be then a line around here. Okay? Let's say it's this line. So we define a vector. And then projecting the original data onto the principal components, let's say this first principal component will give us an approximate representation of the data in fewer dimensions. So if we do a projection of all the data we have on that vector, we are approximating our 2D data with 1D. And this is equivalent to rotating the data on the new basis, then throwing away every other dimension that is not necessary or just noise. And equivalently, we want to minimize the orthogonal projection error. So we want to find the best possible fit line here that minimizes orthogonal projection error. Okay? So next step will be find another line orthogonal to the first one that with the maximum projected variant from it, which will be something like this. Okay? And it's orthogonal. And we repeat that. Let's say we have a higher dimensional data set. We repeat this until we have k orthogonal new lines. And each of them trying to encompass the most variability as possible in the data. So the projected position of a point on these lines will give them the coordinates on the new k-dimensional reduced space. Okay? So what it gives us are principal components. These vectors are then ordered. The first principal component have the most variance, and the second have the next most variance, and so on and so forth. But they are also uncorrelated because they are orthogonal by definition. So your original data may have correlated features, but not those after principal component analysis. And the PCA algorithm looks like this. So for input data, we'll have, let's say, our data matrix, X, and let's say we provide a given number of dimensions, smaller than the number of dimensions originally we have. And as an output, we will have a projected matrix on K dimensional space. So basically what the algorithm is going to do, the first step on the PCA is calculating the covariance matrix between each dimension of the data. So instead of having, let's say, features in the columns and observations or different samples in the lines, I'm going to calculate a covariance matrix, okay? So covariance matrix is by definition centered in the origin. So instead of having features and observations, we'll have feature by feature. And we do that calculating something like this. And in this case, the X with a dash on top means the median, okay? And we're basically removing or subtracting the median from each of the variables, so X and Y. So this is basically one cell of our covariance matrix, which will measure covariance between the variables X and Y. What is the effect on a given distribution by subtracting the mean or the average? Let's say you have a normal distribution with an average of mean of 3. What happens if I do this bit here? Yeah, so I centered it to the origin, to 0. So PCA requires that the matrix that you import is centered to 0. That's done by this bit here. And then you calculate covariance. And then you find the eigenvectors of the covariance matrix. So we talked about eigenvectors last week, and when we talked about eigenvector centrality. So when we find eigenvectors via a matrix operation, that finds basis vectors, which are uncorrelated, are orthogonal vectors, and we'll also find eigenvalues. And these give a measure of variance along each of the new dimensions of the data. And then we just need to choose K, and which are how many principal components we want to keep. And next thing we do is we are going to project the data on these new eigenvectors, on our new space, using K-base vectors, K principal components, and then we have our output matrix Z. So the principal components chosen are then the eigenvectors with largest eigenvalues, meaning those that represent the majority of the variability of the data. Okay, so eigenvectors then, if you recall, for a matrix, let's say a feature matrix A, there is a vector X, which is an eigenvector, such that the product AX is equal to a scalar multiplied by X. So there's a lot of matrix operations to find that, which we'll not cover here. So you end up with your different representation of the data. And the next question we need to ask is, okay, same thing with K-mean, same thing with any parametric algorithm. What's the number of dimensions we want, or what's the parameter we're going to choose? In this case, how many components? So if we start, let's say, with 60 dimensions, how do we choose the number of dimensions we want on our derived data? And one way to do that is actually checking the distribution of eigenvalues, because they tell us about the variability and the variance explained by the eigenvectors. So let's say in this case, the first eigenvector explained, let's say, 37% of variability, or variance in the data. So let's say we can then choose K, or choose the number of eigenvectors to cover most variance in the data. Let's say 90%. So in this case, instead of considering 60 dimensions, we can represent 90% of variability with something around 8. So it's 12-15% of the original data, and we represent most of the information we have there in terms of variance. And the time complexity for principal component analysis is mainly dependent in 2 steps: generating the covariance matrix, which is quadratic in the number of features. Of course, we have and we end up with a matrix n by n times the number of observations we have, and the eigenvector decomposition, which is cubic. So PCA is mostly cubic, depending on the number of instances we have. So it's not a very effective or scalable algorithm, but it's very, very important and very effective. Are there any alternatives? And of course, the question is there are. And one of them is singular value decomposition. It's also a very famous method as well. So it's a more efficient algorithm, with a lot of efficient implementations available as well. And interestingly, singular value decomposition can be used to compute principal components. So you can use SVD to calculate PCA. And singular value decomposition works as follows. Let's say we have our inputs matrix. In this case, it's a matrix of items and subjects. Okay? It doesn't matter what's the meaning of our coordinates here. So what we're going to try to do is, let's call this matrix C, and it has m lines and columns. What we try to do is decompose this matrix into three matrices, okay? Where we will have U, sigma, and V transpose, where U is and V are orthogonal eigenvectors, and sigma is a diagonal matrix with singular values. So this is a very similar procedure as calculating eigenvectors from PCA. And in this case, the difference is that the singular values are the square root of the eigenvalues, okay? And then we can then reduce dimensionality by selecting a subset of eigenvectors and eigenvalues, or in that case, singular values and singular vectors. And this is more efficient than PCA because it doesn't require the calculation of covariance matrix. And on the other hand, we can use SVD to calculate PCA as well by solving the equation, U sigma V transpose. And of course, if C is centered, and we will have V, in this case, with the principal components of our eigenvectors, sorted from largest to smallest eigenvalues. And let's say if we select the K columns as our principal components, we do dimensionality reduction. Okay? So PCA and SVD. So we can, as mentioned, we can use SVD to calculate PCA. So we can interpret PCA as an SVD on a centered covariance matrix. And SVD doesn't require to calculate the covariance matrix, so it's a bit more efficient, and it has been used in a lot of different applications, for instance, in image compression to remove noise and so on and so forth. For instance, you have your original image with 264 components or features, let's say the number of lines of the picture, and you can, using just a subset of those, let's say 22, you can recover most of the patterns there. So using 10% of the data, you can recover most of the variability. That's one of the powers of this kind of technique. So it has been used in different biological setups as well. For instance, analyzing microarray data, where you have your eigenarrays and eigengenes associated between them. But one interesting thing you can also do with PCA is project them like this. So this is a very usual plot when you're doing PCA analysis, which is plotting your first with your second component. So let's say you have 100 different dimensions. You reduce it to 2. And one thing it gives you is the projection of the original features on these 2. So what it gives you, for instance, is the importance of the original values in explaining variance, which can help you understand better your data as well. Okay? For today, that's it. And on Friday, we'll focus on different alternative approaches for feature selection and feature extraction as well. Okay? Thank you very much.
PCA is yeah, basically, I don't understand this, the second PCA.
Yeah. So what happens is the following. So
Yeah.
the first thing you need to do is test the question. Which direction explains most of the variability? Okay, in this case, it's just 2D, you know, it's that way,
Yeah.
right?
Yeah.
So then you have your first principal component, which is vector Z.
Yeah.
You can do PCA two ways. You can ask the question now based on orthogonal vectors from Z1, which one explains the most variability? And in that case, let's say it's that one. It needs to be orthogonal. Because one of the principles of PCA is, or we end up with completely unrelated variables.
Yeah, yeah, yeah.
So they're not related at all.
Yeah.
So in this case, for instance, it's that way. It could be that way.
Yeah, yeah.
It could be, for instance, that way. They will still
So
be
it's-
orthogonal.
yeah.
But instead of checking what it does, we do this via a very elegant matrix multiplication or decomposition. So that's how it gives us all of the directions.
I didn't get it.
What you generate?
I
The
didn't-
first one, or how you generate this line?
I think I don't understand why it's maximizes the variance of the project.
Why it does? Or
I
how
can,
it
I
does?
can understand the first principal components is justifying the direction with the highest variance, right? Biggest variance, and the second one is to
Or, alternatively, other way to see it instead of maximum variance is minimum projection error.
yeah.
So let's find a line here where the projection error is minimum. That's a different way to see it, but it's the same concept. Okay, so in that case, Z1
Yeah.
is the line that minimizes the error when I project the data from 2D to 1D. Let's say we have something 3D here, and then we find the next one. It's the orthogonal one that will also minimize the projection of the remaining data to this one.
Remaining.
Or that in that
In
direction.
this case, it's a 2D.
In that case, it's 2D, so it's a very difficult one because we need a multi-dimensional one to actually explain. So if you go to the next one,
Yeah.
so, and the next one. So the next one, you have the two principal components there. That one is quite clear, right? So if you start with a matrix of dimensionality n, you end up with n principal components, okay? The number of principal components equals the number of dimensions you have. So these are the only two components you have, okay? That one and that one. So I'll also do the same. So I need to project the data here as well. If I show you a 3D one, there's a 3D one somewhere in the beginning, sorry. So for this one, for instance, let's say most variability starts from that angle first.
Yeah.
And then I need to find the other one that is orthogonal to this one. So I need to find things that goes here
Yeah.
to minimize the projection error or maximize the variance. In that case, if you have, so it's a 3D plot, right? But all your points are in a plane.
Yeah.
So when you do this one, you're minimizing the projection error. When you do this, when you do that one, you're minimizing the projection error doing this. So that's why they're the best ones. So if you have coplanar points, you only need 3, right? 3 points there form a plane. That's a minimum number of points in 3D. And basically you need to find one component that will cover 2 of them and another one that will cover the other one.
Yeah.
So
yeah,
if you
yeah,
have, so if you have this point, and this point, one of them will cover this point, this, and the other will cover this. Make more sense. Two ways to see it: either the minimizing the projection error or maximizing variance.
Oh, so that's the same.
It's the same.
Yeah. So in this case, in the 3D, we will have three
principal components.
So what is the third one? What is the third?
If it's
Is it the direction that like a,
let's say R. So let's say we have X, Y, and Z,
Yeah.
and this is our plane,
Yeah.
right? So one component is this one,
This one.
and that one.
Yeah.
We have a third component where it needs to be orthogonal. We don't have an option, so it
Yeah.
needs to be here. That's the only orthogonal one we have.
But we don't do the calculations on the last one.
We do it, but the variance here is 0. It's
Yeah,
adding
there
nothing.
is- yeah.
Basically, it
Right.
says when you have something in a plane, you don't need a third dimension because it's a plane, so it's a two-dimension thing. But yeah, we still do have it, so it's that way. But it's the length of it is 0,
Yeah. Okay.
so it's not explaining any variance. There's no variance there,
Yeah.
but it's still there.
Yeah.
Does that make more
Yeah,
sense?
it makes
It's a very difficult concept to grasp, but
So sort of, it's hard to grasp. Yeah. I have another question as well. How is this? I haven't done linear algebra before, so
oh, you haven't. Okay.
yeah. So I don't understand what are these three matrices.
So when you do matrix multiplication, so you can I write?
Yeah, you can.
So matrix multiplication works as follows. Let's say we have X, Y, Z, W, A, and B. Let's say we have two square ones. A, B, C, D, F, G, H. You can only multiply. This is 2 by 2. This is 2 by 1. So you can only multiply if these values are the same here. Oh, sorry, that one.
Middle one. Yeah.
If the value, can you go back? I made a mess. How do you go back? Thank you. If these two are the same, you end up having
Oh, it's gonna be 2 by 1.
okay. So they need to be compatible, and you end up with something different.
Yeah.
2 by 2, you end up with a 2 by 2.
Yeah.
So, and how it works is I, in this case, will be x times a plus y times b. J would be z times a plus w times b. Okay? For matrices, we multiply this by this. That's this guy here. We'll multiply this by this. It's this guy here. This by this is this one. This by this is this one. That's how we do matrix multiplication. And that's why you have this here.
Yeah. R.
And R with n.
Yeah.
And if you multiply all of them together, you end up with an n
N
times n,
n.
which is the original one here.
Yeah.
So basically, we're decomposing it.
Yeah.
And there are a few matrix properties that are interesting. So let's say you have a matrix A. If you multiply it by the transpose, what's the transpose? So let's call this one here RA. Okay? A transpose would be change lines with columns. So it would be X, Y, Z, W. So when we multiply this by this, A by A transpose, we have the identity, which is a diagonal one with ones and zeros. Yeah?
Yeah.
So there are linear algebra. It's a long subject. So when I was in college, linear algebra for me was 64 hours of lectures. So 4 lectures a week for a whole term. And that's just linear algebra. Doing matrix multiplication and vectors and blah, 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 blah. Determinants. So there's also something called determinant of the matrix and so on and so forth. That's not relevant for this. So this is how you do multiplication. That's why you end up with this. So there's an algorithm to how to divide them.
Yeah.
Okay?
Yeah.
And the thing is, the singular value is a diagonal matrix. A diagonal matrix, the diagonal have non-zero elements and everything else is zero. Okay?
Yeah.
And each of them in this case, it's called a singular value. And it's basically the square root of the eigenvalues from the PCA method, which is similar. They are both related with, I can send you some material if you'd like, that actually explains how this linear algebra is done.
Yes.
If you want to just send me a message, I'll send you a set of slides.
Yeah.
But it's a lot of mess. Anyway, so this is a diagonal matrix which will tell us the importance of each of the vectors. So in this case, this will be a vector, eigenvector of items, and this will be a vector of subjects. So the interpretation of the SVD is we'll have here eigenvectors pointing to items, which are their vectors, right?
Yeah.
Eigenvectors pointing to subjects. So if I want to reduce dimensionality, instead of having 5 subjects, I want 2, I'm going to choose subject vectors, 2 subject vectors, and 2 singular values. So I just multiply this by this, for instance, and then I have a smaller dimension.
Yeah.
Okay? That's the basic intuition. And then you have an algorithm to actually go from here to dividing this, okay, which is cubic as well. Okay? Which is basically, if I recall, I don't recall, it's multiplying x times both. No, I can send it to you, the actual algorithm. So how you go from here to here. So this algorithm here, if you'd like. Just remind me with the message. Yeah. And maybe it will be clearer.
Yeah.
But I thought it was a bit of a waste of time to try to explain this. This involves a lot of algebra. So
Sure.
yeah, the important thing is knowing when it works, when it doesn't, how you use it, what can it do for you.
Yeah.
Okay? Issue with SVD and PCA, you end up with a completely different universe of a search space. So interpreting what your PC1 means, that's difficult, right? So PC1 is a linear combination of all of them. Okay? You can express PC1 as, let's say you have DCCLT, so D times a constant A plus C times a constant B, and so on and so forth. So a linear combination of all of them. That will point to the new PCA1 in maximizing variability. Okay? So interpreting this is quite hard because it's not your actual original data. It's a linear combination of your original data. Okay? Did that help? I hope so.
Yeah.
So can we explain it as how much one? Sorry.
It's difficult.
Yes.
I mean,
So a lot of people spend a lot of time trying to interpret SVD components, which is more complicated than PCA. PCA at least gives you those that last plot. The last plot that shows that PCA1, PCA2, and on PCA1 here are the projection of the original features. So you know how important are the original features for PCA1 and 2, and the most important ones, then you can infer that they are representing most variability. Therefore, they're important. SVD is a bit trickier.
it's a combination. It's a linear combination of all the features. So you can explain it as how much one feature contribute to this.
So the PCA1, for instance, how much each contributes. And it's a linear combination of all of them. So even if it's multiplied by 0, it's considered. Okay?
Yeah.
And then you...
But it does not contribute to the final PC, the most important component.
The most important component will be a combination of all of them.
But maybe one of them, the constant is 0.
Yeah,
Then you...
sure. And one of them, the constant could be the highest possible.
Yeah, so I mean, so how important they are contributing to it.
So let's say it's a PCA1, it contributes to 90% of variability. Okay, let's consider that. 90% of variability in one variable. Okay, let's consider that. And out of those, you have three features which have really high weights. on this linear combination. And the rest is really, really low. So you can say that most of the variability, 90%, is obtained with 3 original features. That's the kind of interpretation. But these graphs you can extract straight away from